All right, so we're going to find and use inverse functions. So first of all, let's talk about what an inverse function does in the most general sense. So in the most basic terms that we can explain it, inverse functions are functions that reverse each other. So what you're doing is you're switching your x and your y values. So for example here, we have a mapping of this function f. And the way that you describe a mapping is it takes 1 and maps it to x. You take 2, it maps it to z. 3, you map it to y. Now, we're probably more comfortable with points, so you can list these as points. You've got 1x, you have 2z, and we have 3y. Okay, so the first numbers obviously are our x values, and the second, in this case, they just used variables, but those are our y values. Okay, so if we want to talk about the inverse of this function, you can see the notation there. It looks like a -1 exponent. It's not a -1 exponent. You read that as f inverse. Okay, it's not a -1 exponent. That's f inverse. It will reverse that mapping. So it just switches what were our x's are now our y's, and what were our y's are now our x's. So it just turns them around. So instead of having 1x, we have x is being mapped to 1. Instead of having 2z, we have z is being mapped to 2. And instead of having 3y, it is now y is mapping to 3. So it's just switching the x's and the y's. Okay, that's all a mapping does, is it switches your x and your y. Or excuse me, that's all an inverse does, is it switches the x and the y values. So we can see that in a mapping. We can see it if we arrange the points as coordinates. We could also put those points in a table and see it there as well. So let's look at this question. Which of the following is a true statement? The domain and range of f are the same as the domain and range of f inverse, or the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Which do y'all think, A or B? B. We're switching. It doesn't make sense that they would be the same because we switch things around. So B is the true statement here. I want to go back to my mappings here. I labeled them with x's on the left and y's on the right, but let's also go back and remind ourselves that really we're talking about domain and range. Okay, we traditionally think about the domain as the x's and the range as the y's, and that is true, but the domain of this function f would be 1, 2, and 3. We don't know about any other points. All we can see here are 1, 2, and 3, and we know that the range is x, y, z. 1, 2, 3, and x, y, z. And then when we talk about its inverses, or its inverse, it switches, and the domain is now x, y, z, and the range is 1, 2, 3. So, very basically speaking, your inverse switches your domain and range, or it switches your x's and your y's. It just reverses those two relationships around. All right, now let's look at what we would consider the formal definition of the inverse. Let's throw some more function notation to this. F of A is equal to B, so that is on the original. So if you want to think about it this way, A is your x value, B is your y value. If you want to arrange it as a point, you would have the point AB, because A is your x, B is your y. You could plot that point on a graph. Okay, so in inverse notation, it switches the x and the y. So now that number that was B is now the x value, and the A is now the y value. So on the inverse, you have the point BA. On the original, you had the point AB. On the inverse, it's going to be the point BA if it's the inverse function. So let's look at this from a mapping perspective first. Here's another mapping that we have. We have all numbers this time. It says, suppose the function h is defined by the mapping above. What is h inverse of 9? Okay, H inverse of 9. Well, that's the x value of the inverse, x value of the inverse. So what value would that be on the original? That would be the y value of h. Okay, the x value of the inverse is the y value of the h. So we go to our h function. We've got x's on the left, y's on the right. We look for the y value of the original function. That's the x value of the inverse function. So the answer to this question is, what does it map to? It maps to 6. H inverse of 9 is equal to 6. Because on the original, we would have the point 6, 9. So on the inverse, we have the point 9, 6. We're just flipping the places there. Okay, we're just switching x and y. I need to clarify anything there. Makes sense. Okay, so let's check your understanding. There's a different mapping. Independently, what is G inverse of 3? Okay, G inverse of 3 would be, yes, -1. It's the x value of the inverse, so you're looking for where is it a y value on the original. Go backwards, it would be -1. Okay. All right. Going on through. So let's take it from a mapping to, well, what if we're looking at the graph? Okay, again, there's nothing different. Okay, there's nothing different. We're just looking at this in a different representation. So the same principles still apply. If we need to find, we're looking at the graph of G, and we want to know what's G inverse of -7. Well, again, if you have to write it down, do whatever you have to do. -7 is the x value of the inverse. So that means it's going to be the y value of the original. So we go to the graph of the original here. -7, a y value of -7 is down here. We go to where that occurs on the graph, and that occurs at -3. G inverse of -7 is -3. Because if it's the x value of the inverse, it's the y value of the original. So find where you have a y value of -7 and find its x. Okay, individually, you've got another graph there. You have a graph of h. It's just a linear function. Individually, I want you to decide what is h inverse of 4, and then we'll check it with everybody here. We get -2. Okay. You find the y value of 4. Go over to where that occurs on the graph. Find its x value. So -2 is the correct answer to that. Okay, so let's look at it from another perspective. Let's look at it from the equation perspective. If we are given the equation of the original function, f of x is 3x minus 2, what is f inverse of 7? Now, do we have to look at the graph? We could. What could we do instead of looking at the graph? Solve it. Okay, so are we plugging in 7 into the original, or are we setting it equal to 7? Equal to 7, because this 7 is the x value of the inverse, so it's the y value of the original. f of x is just a fancy way of saying y. So we set our equation equal to 7. It's the same thing that we just did with the graph, guys. We were finding the y value and trying to find out which x value gave us that y value. We're doing the same thing here. We're just doing it algebraically. So we add 2, divide by 3. So f inverse of 7 is positive 3. All right, any questions so far? Let's look at what we've got here. Consider function f given in the graph, and we have a table of select values. Now, it's not all the values here, but it is select values of f. We're going to graph the inverse. Okay, we're going to graph the inverse of this. So we're going to graph it on the same xy axis here. So if our inverse switches x and y, so if the original has the point, I'm just going to start with the first one in the table, -2, 1/4, the inverse switches those around. So the inverse is going to have the point 1/4, -2. So we're going to have a point about right there. If the original has the point -1, let me do this over here. Write it down so you can see as well. Okay, we're just switching the x's and the y's. So the second point there is going to switch them. So it's going to be the point +1/2, -1. The next point is going to be the point 1, 0. So our x is 1, our y is 0. The next point is going to be 2, 1. And the last point there is going to be 4, 2. Now, there's nothing special about the points here that were chosen. We could have picked any other number of points there as well. We were just picking a select few. And then it's going to have a similar shape, so go ahead and connect those dots there with a curve. And now notice how, now I don't have a lot of detail right here past that 1/4. But it should mirror kind of what's going on with the function. It doesn't, dive down really sharply over here. It just kind of hugs the x-axis. So inverses, since they're switching x's and y's, they kind of, they're switching places of everything. So if that one's hugging the x-axis, then this one should kind of hug the y-axis. And then similar up here, I can kind of just continue my curve a little bit past that point. So this is f inverse of x. Now, I didn't put this graph on your paper, but I want you to see here. Do you kind of see some symmetry maybe going on here? I was trying to point that out. Similar shape, okay, the way it's getting close to the axis here and there. Here's the exact same function, okay? Same function, just with a little bit more detail without the specific points. It also has the line y equals x graphed in there. If you turn your head so that the line y equals x goes straight up and down, you should be able to see the mirror reflection of the purple graph versus the teal graph here. If you turn your head to this line, y equals x is straight up and down, you should see that they are mirror images of each other. So here's a property of the inverse. A function and its inverse, okay? F and f inverse are reflections across y equals x. Every function and its inverse will be a reflection across the line y equals x. So it doesn't matter what function we're dealing with, whether we're dealing with a linear function, this is probably some type of exponential function, or actually it is an exponential function, the one that we're looking at right here. It could be a polynomial. It doesn't matter what function you're talking about, but a function and its inverse are always going to be reflections across the line y equals x. Okay, so last thing here, check your understanding. That last graph that you've got there is h of x. Graph the inverse. Okay, graph the inverse of what you're seeing right there.